So in 3.6, which is what we're going to start today, which is the inverse functions and chain rule, we'll do a little bit of review, a little pre-calc just to remind ourselves of what these inverse functions are. So first, the notation. If I have f of x, then I know that f inverse of x is written like so. I also know that for every point AB on f of x, the inverse will always have the point BA. The x's and y's are interchanged. So here's an example, let's say, of this cubic graph, and this would be the inverse. And you might remember that symmetry, that those two graphs are always symmetric over the line y equals x, and it's because your x's and y's are interchanged. They flip. So there are a couple of other pieces of information that would prove to be useful before we jump into the calculus of all of this. One of them being that if f and g are inverses, so if they're inverse functions of each other, what do we always know that f of g of x equals? Yes, and we also know that if we did the reverse of that composite, that g of f of x will always equal f. And it's because one does and the other one unravels, and so you're left with that pure x. So we're going to be using that method to solve for derivatives of specific functions. So you might remember that if my f is e to the x, its inverse function is the natural log of x. So I know if f is e to the x, f inverse is ln of x. So that's why, folks, this statement is true. So we're going to use that true statement to prove or to discover what the derivative of ln of x is. Let's get to work. So let's look at this true statement above, and let's first take the derivative of both sides. If those two functions are equivalent, or if the left and the right side of the equation are equivalent, then taking the derivative of both of those should also be a true statement. So the derivative of, I'm going to start with the right just because it's easier. The derivative of x is 1. What's the derivative of e raised to some g of x? Well, I know that the derivative of e to the g of x is itself times g prime of x. So let's do that same method on the left. So it would be itself times, well, we don't know, the derivative of ln of x. I do think it's clear to us, though, that this piece right here is what we're trying to isolate. So let's continue. So I think our next step is, let's get that by itself. Let's divide both sides by e to the ln of x. And that allows us to get the derivative of ln of x by itself, so that's isolated. And we notice that it equals 1 over e to the ln of x, which would be our answer, but let's clean it up. And so there we have it. The derivative of ln of x is 1 over x. So we're going to use the same concept to find the inverse, the derivative of the inverse of sine and tan. So let's first start you off by some trig review. And I'll go back to degrees because it's more familiar, but that's pi over 6. All right, if I know that sine of 30 is 1/2, sine of 30 degrees is 1/2. I also know that inverse sine of 1/2 is 30 degrees. And that, again, is us playing around with the fact that for every AB, the inverse contains the point BA. Never mind that we are restricting our values for sine to -90 to 90. That's not relevant right here. So, so let's continue. That means for sine of theta equaling some value, I'll just say A for our purposes, then inverse sine of A is going to equal theta. Okay, fine. We'll get back to that. So let's go through the calculus of things. Our first step would be, if I want to find the derivative to inverse sine, I'm going to take the derivative of both sides. And again, cleaner on the right. So I've got 1 on the right-hand side. Now this is a chain rule. Do we remember the derivative for sine of x? It's cosine of x. So we end up with cosine, and there's our nested function, cosine of inverse sine of x, and then I have to multiply by the derivative of the g, which is in blue, and that's what we want to isolate. That's what I want by itself. So we're going to divide both sides by that mess. So we get what that answer would be in its unsimplified form. But let's take a look at this. And keep in mind, this equals some angle theta. So I can rewrite that, because if sine inverse of x equals theta, then sine of theta must equal x. I'm going to go to my trusty right triangle and figure out what the sides would look like, because I want cosine of that angle. So here we go. So there's theta. Sine is so in SOHCAHTOA, so I know that's opposite over hypotenuse. And if I did some Pythagorean theorem, some Pythagorean theorem in here, I would end up with that adjacent side being the square root of 1 minus x squared. So remember, they're asking us for cosine of this angle theta. So now I'm going to look at that right triangle and I'm going to take the cos of it, the adjacent over the hypotenuse. And that leaves us, clean this up, with the derivative of inverse sine of x, that's what's in blue, is equal to 1 over, what is cosine of theta? It's adjacent, which is the root 1 minus x squared, over hypotenuse, which is 1. And there is my inverse formula for sine. You're going to notice that the tan equation looks a lot, or has the same procedure. They don't really ask us to do inverse cosine. I don't know why. But if you were to write it out, it would just be the negative of that one. So I started us off with this one. I'm trying to isolate the inverse for tan. So the first thing we did is we just took that composite function, f of f inverse of x equals x. We took the derivative of both sides. So the derivative of tan is secant squared. So the next step here was writing secant squared of inverse tan of x times, and then in green, the derivative of inverse tan of x. So I hope you'll notice that I want to get green by itself. So we're going to end up dividing both sides by secant squared of inverse tan of x. I'm going to take you over now to the blue side. If inverse tan of x is theta, then you'll see over here on the left, that means that tan of theta has to equal x. So again, here comes our triangle. So there's theta. Tan is TOA. So now I have the opposite. I have the adjacent side. So again, with some Pythagorean theorem work, we know that this equals 1 plus x squared. Now, folks, remember, inverse tan of x equals theta. So I'm trying to find secant squared of theta. Secant is the reciprocal of cosine. So cosine is ca. So secant is going to be the reciprocal, hypotenuse over adjacent, but then I square it. So let's have a look. Secant squared of theta is going to be hypotenuse, 1 plus x squared, over adjacent, which is 1, squared, which would then give us just a nice clean 1 plus x squared. And so, drum roll, we have that our derivative for inverse tan of x is 1 over 1 plus x squared. So then the question is, what is the generic formula for finding derivatives of inverses? And this is sort of a messy notation, but we'll get through it. We're going to use still that same f of f inverse of x has to equal x. So step one, we're going to take the derivative of both sides, which gives us 1 on the right. And on the left, we notice that we get, this is our chain rule, f prime of f inverse of x times what we're looking for, that green, the derivative of the inverse. So our next step is going to be divide both sides by pink. And that takes us here to this step. So let's clean it up a little bit. And there's our formula, that the derivative of f inverse of x is 1 over f prime of f inverse of x. And I sometimes think about pi when I'm thinking about this notation. It's f prime, that's the p, of f inverse, that's the I, of x. So in the denominator, we've got f prime of f inverse of x. So when I'm doing a couple of these examples, let's tease out what we will need from all of these. In this scenario, we are given what f of x is, but we're asked to find the derivative of the inverse of 6. So here is step one. I know that if f contains the point AB, the inverse will contain the point BA. Okay, great. So I'm asked to find f inverse's derivative at 6. So this is 6, some unknown point A. And remember, they gave us information about f. So I know that f contains the point A, comma 6. So I'm going to use that knowledge to go to f and find out what that A value would be. So when would 6 equal A cubed plus 5? Let's solve for A. A cubed would equal 1, so A is 1. So in that case, I know that f contains the point 1, 6, which means f inverse contains the point 6, 1. Great. Let's write our formula just so that we know exactly what we're looking for. So in this problem, I don't know why I didn't give myself more space. They're asking us to find the derivative of the inverse. So that derivative would be 1 over f prime of f inverse of 6. Well, look at what we just found. We found that f inverse of 6 is 1. So we start by just plugging that in to our formula. So that equals 1 over f prime of 1. That's a lot cleaner. So now it looks like the next thing we need to do is find out what f prime of 1 is, because I need its reciprocal. So f prime of x looks like it would be 3x squared, 3x squared. So f prime of 1 looks to be 3. So our answer here is 1/3. Let's look at question 1. They're asking for the slope of the tangent line to y equals arctan. What is that? That's the same as inverse tan of 4x at the point where x is 1/4. So arctan of 4x. I'm just going to write this. So that's like that. So now we want y prime because I want the slope of the tangent line. What would y prime be? That would be 1 over 1 plus x squared. But oh, it's not just x. It's inverse tan of 4x. So this is chain rule. So it would look like this. 1 over 1 plus 4x quantity squared times the derivative of that g function, which is the derivative of 4x. So let's just clean that up because I know that that's 4. And so we've got this, folks. That's my y prime. They're asking us, what is y prime when x is 1/4? So now I'm plugging in 1 plus 4 times 1/4 squared. Bringing it down here, that's 4 over 1 plus, oh, that's just 1 squared. 4 over 2. So my answer is D. All right, let's try question 2, where we're given a function that's differentiable, and they gave us these two ordered pairs. F of 3 is 15, f of 6 is 3, and we know the derivatives at 3 and 6. Then they're telling us that this g function is its inverse, that g of x is, in fact, f inverse's function. And they're asking what is the value of g prime of 3. I might first start with just a table of values that we know of f. We know 3, 15, and we know 6, 3, because that also tells me information about the inverse. That means that the inverse must have, we switch those two, the point 15, 3, and 3, 6. Keeping in mind, that's also my g. So they're asking for g prime of 3. So that would be 1 over f prime of f inverse of 3. So do we know what f inverse of 3 is? Yes, we do. So I know that I can replace f inverse of 3 with what it equals. It's 6. So this now becomes 1 over f prime of 6. So now we've got to look at the values and see, do we know what f prime of 6 is? Well, we sure do. It's right there. It's -2. So that gives us 1 over -2. And that's letter B.